So I'm Sally McFarlane from Department of Energy. I am one of the co-leads of I always have to look it up, Monitoring, Observing, Modeling, and Prediction, or MOMP, collaboration team. I also have co-leads David Allen from NOAA, who is attending today, and David Clemens Sewell and Kiki Schultz, who might be able to join us. We're not quite sure. But the four of us are the MOMP co-leads. And so for those of you who might not be so familiar with IARPIC does have a research plan, and it has objectives and deliverables. And one of the deliverables that MOMP supports is about supporting development of synthesis products, best estimate data sets, and model intercomparison studies using cases from major Arctic field campaigns and long-term observational sites to better enable the use of observational data in model evaluation. So along with our colleagues in the observing and modeling teams, we've been doing a series of webinars on forging better connections between models and observations. And so this is one of those series, and it's sort of a follow-up to a webinar we had a few months ago that also looked at some aircraft research campaigns. So as I'm sure you all know, since you're here, but airborne field observations are critical for improving our scientific understanding of Arctic processes and for informing model representation of those processes. But it's not always straightforward to couple aircraft observations with models. So it's useful to think about how to connect those both before, during, and after those campaigns. So in this session, we're going to hear about two different campaigns that are in very different stages. We will hear about the CAESAR campaign, which occurred in 2024 and focused on marine boundary layer clouds during cold air outbreaks, and then Snow for Flow, which is in the planning stages and will focus on Northern Hemisphere glaciers. So it'll be interesting to think about, how we connect with models both after and before the field campaign planning starts. So our first presentation today will be by Paquita Zuidema from the University of Miami. And I will ask, we will have a discussion period at the end. You can put some questions in the chat if you have technical or short questions for Paquita after her presentation, and then we'll save the longer discussion for at the end. So with that, Paquita, please go ahead.
Okay, yeah, thank you, Sally. So let's see. Here we go. And it should be in slideshow mode. So
Yes,
cold air outbreak experiment in the subarctic region, or CAESAR. This used the NCAR C-130 plane. We based out of Kiruna, Sweden in around March of 2024. And yeah, this is a photo of it landing right before the campaign started. We joined there's been a number of high latitude campaigns in recent years that have been asking similar and related questions on, how the small scale processes that contribute to Arctic amplification, and questions that you really need aircraft for are how aerosols, either the cloud condensation nuclei or the ice nucleating particles, modify cloud fraction and longevity, and then how that feeds back onto the surface radiation balance and turbulence structure. And the internal cloud processes, how those modify cloud fraction and longevity. I'm also, again, thinking of turbulence and secondary ice production processes. So the main idea there is that when you have more ice, the clouds tend to not last as long, or that's kind of the governing idea. And then how changes in these processes feed back on snowfall and extreme events. So we did 8 research flights over this time period. And a feature of the C-130 is, you could see in that photo, it's like a bumble. It's an ex-military transport plane, so it has pretty long range reach. So we were able to reach the Greenland marginal ice zone with that. And we were lucky with well, the year that we went there, the um, Greenland ice zone bounced back a little bit, so there was more. The sea ice extent was a little larger than it had been in some of the previous years, and that reflected the synoptic conditions that we encountered. That there was a lot of air coming down the Fram Strait that was cold, and the thermodynamic response of the ocean was pretty fast, letting it to the sea ice grow back. Um, we had a comprehensive suite of instruments, and so that's also a nice feature of these C-130 planes. They're kind of like big bumblebees of planes, and you can really put a lot on them. So, in addition to kind of standard ice microphysical measurements, we also had a holodeck, which gives you a sense of the spatial distribution of the ice and liquid particles, and a FIPS that came from Germany that takes these really beautiful high resolution images of ice particles, and a good aerosol and gas suite of instruments. Colorado State University was responsible for doing the ice nucleating particle measurements, and um, so they were on top of that. And we also had good isotope measurements of the water vapor. So the remote sensing suite was also very nice. In particular, we had Shen Wang deployed a Raman LiDAR looking down that was able to profile the water vapor and the temperature profile. And in addition to that, we had up and down looking cloud radars and upward looking LiDAR and upward looking microwave radiometer and an additional um, cloud radar at a longer wavelength to get the larger ice particles. These were hypotheses, and because we had such a large suite of instruments and that long fetch, we were able to have a pretty comprehensive suite of objectives to go after. The first one was looking at the exchange between the surface with the boundary layer above it. The next three have to do with aerosols and clouds, their interactions, the cloud longevity and how precipitation is produced and how that organizes the cloud field. And then the last one is on polar lows. So polar lows are like little intense mini hurricanes that can happen at the higher latitudes that can be quite upsetting to the coastal communities and to shipping traffic. What I'm showing at the bottom is the typical flight plan that we did, where we would fly high and use the remote sensors to understand what was below us, get a sense of where the cloud top height was, where all the liquid was. Then, when we got as far as we could on that flight, do a slow descent down to that furthest point, and then come back, um, profiling the clouds and getting information closer to the surface. These are the people that were involved. Bart Hertz, Greg McFarcar and I were in the leadership of this. And then we have, let's see, so modeling has come up here. We did not have dedicated modeling effort, but we did have, they're just, the funding limit on the campaign was such that we were asked to exclude that. But we did have some funds to be able to bring people to the field and the modelers and to try to keep that conversation going. So those are listed on here as well. And we also collaborated with people at Met Norway and brought in people from Sweden, both for their expertise, but also to try to expand the extent of this campaign. So this is a summary slide. This is the one I'm going to spend the most time on, I think. So most of the cloud tops that we measured were at temperatures that were colder than about -15. And in panel B, you see this structure that wasn't unanticipated, where you have more liquid at the colder temperatures. So that's a bit counterintuitive. Why is that happening? And that's something that the models really struggle with. Panel C shows the droplet number distribution, and Arctic clouds mostly are pristine, but we actually did have some clouds that had that were a bit polluted, so that was interesting too. And then the distribution of the liquid water path in these cold clouds, which is of interest because how is that liquid getting maintained? Then that panel D shows in green and blue shows the ice nucleating particle concentrations. They're pretty low, one per liter or less. And in the red, you see the ice particle concentrations, so the number of ice crystals that are actually getting produced. And from looking at this graph, what you would think is that at the coldest temperatures, that the ice crystal number concentration is matching that of the aerosols able to nucleate them. So the primary ice nucleation. And then it does grow a bit. There's more ice crystals at warmer temperatures, maybe because, well, they're falling, or maybe there are some secondary ice production processes. An interesting thing about these cold temperatures is that in models, the um, secondary ice production process that is most likely to be represented is this Hallett-Mossop process, which I have in that green box with an X through it. That process is only active at warm temperatures, so warmer than about -8. So the fact that we were outside of that temperature range means that these one of these other five processes had to be active to the extent that we were getting additional ice crystals. Okay, 3 flights reached the Greenland ice, and one flight in particular is our golden case, the 16 March case, where we ended up over sea ice that was 100%. So that would be a nice subject, I guess, for a model intercomparison or some larger modeling focus. Yeah, this was our iconic flight. So you see all the dropsons being shown there, and the structure that you would expect, where as you get towards the sea ice, it just becomes more stable. This is just a neat observation, I thought. So this was on the flight back, and um, initially the aircraft was above the mixed layer that's connected to the surface. But as soon as we were able to be in the air layer that was connected to the surface, we started to see ice particles already. And this was at a temperature of about -25 degrees or so. So it's telling us that the vapor that's coming, yeah, you can see there's some clouds in the background there, that the vapor that was coming out of the open leads, there weren't very many yet at that time, but there were some, where was immediately going from vapor to ice. So that's interesting. Okay, I'm just looking at the time. We have our science team meeting on Sunday in a few days in Madison. These are presentations that are being provided there that just give you a sense of where the work is at. So this campaign was 2 years ago. We're still coming out with the papers, the analysis. The second presentation on there, Shao et al., is focused on this iconic case, and I think is also starting to look at this modeling simulations from that. The other talks are all observational analyses yet still. We still have quite a bit to do, actually. We do have a BAMS paper that is providing an overview of the campaign that just came out and as an early online release. And so all the data is available. Some of it is still getting polished a little more. We want to develop these value-added products that would be more easily, well, that are just more useful to the modelers. Um, it's, the data is easy to get hold of. We had a nice outreach component that was led by people at NCAR. They made these really beautiful videos. It's a very photogenic area, as you all know. We are also working with the larger aircraft community to coordinate. So not every single aircraft campaign, it can't really gather enough data sets to develop a model parameterization of its own. I think we're moved beyond that, and we're still learning how to um, combine and work with all our different data sets. And so Harold Sodeman had a nice workshop that was in early June that got people together from these different campaigns, and those conversations are continuing. They'll continue on in Madison next week. There's another conference happening next March that will be another opportunity to keep these conversations going, just keep that momentum going. And that is okay. And that's kind of the end. So yeah, I mean, this is my first IARPC meeting, and I'm definitely, well, not just me, but there's a lot of interest in expanding the impact from all these aircraft campaigns because they are expensive and we need to get as much out of them as we can. So thank you.
Great. Thank you very much, Paquita. Again, we're going to save discussion for the end, but if you have some questions, you can go ahead and put them in the chat, or we'll do raised hands at the end to have the discussion. If you have just a quick technical question for Paquita, you might put that in the chat too, and she could reply. Okay, thank you, and thanks for staying on time, which is great. So we will move on to our second presentation, which is by Lauren Andrews from NASA Goddard, and she will introduce us to snow for flow. And you're on mute. But
There,
we can
now
see
you
your
should be able to
slides.
hear me. Yep,
Yep.
great. Okay. So thanks for the invitation to talk about our upcoming campaign. So Paquita gave you a really nice overview of a mission that's been completed. And Snow for Flow is a mission that was selected a few years ago, and we are very much in the spin-up phase with our first airborne campaign and ground campaign happening in the spring of next year. So this talk and sort of the slogan really for our entire mission is an airborne mission to measure and model the state and fate of Arctic glaciers. And that's really how we view this mission, right? That it's both, an airborne and a ground campaign, but also a modeling campaign to improve our understanding of glacier state and glacier fate throughout the Arctic. And our principal investigator is at the University of Arizona. It's Jack Holt. Myself and Joe McGregor, who actually is also online, are the deputy PIs on this mission. And then Albert Wu is our investigation manager. And then we have two deputy investigation managers, Peter Griffith and Dan Hodgkinson, who are both, all three of those people are at Goddard. So what really motivated us to sort of develop this mission with a large group of people is that Northern Hemisphere glaciers are a very small amount of the ice volume globally, yet they contribute a large amount of current sea level rise. And this mass loss is really expected to increase, changing our coastlines, our ecosystems, and increasing the freshwater input into our ocean, altering sea level. But our ability to project the magnitude of that change is vastly dependent on our ability to model the current state of those glaciers, so what their current volume is now and what their current volume will be in the future. So we have to have really great understanding of what the geometry of those glaciers are and what that snowfall and that runoff is of those glaciers. And we simply don't have that. And I'll provide some really nice examples of that next. So when, snow for flow is this sort of amalgamation of words, but it really means that we want to understand the snowfall that accumulates on glaciers and regions of Greenland, and understand the flow of those that ice. So here is, two plots that, simplify, understand, or just simply motivate what we're doing. So here is the climatological precipitation over the seasons across Alaska from a variety of models and satellites. And you see that the daily precipitation rate, there is a massive spread. And so when you have this large range in precipitation, you have large range and uncertainty. And this, translates, across the Arctic. We see this in Greenland. This is a really great example from an older paper by Laura Koenig that looks at Operation Icebridge data. And it's looking at radar-derived snow accumulation rates and comparing that to modeled snow accumulation rates in the MAR regional climate model. And you see, particularly along the edges of the ice sheet, that we're seeing up to a meter of water equivalent difference between what is being measured by radar and what is being modeled. So we have large uncertainties between our models, between our observations, a large spread in what is being estimated. And when you have large uncertainties, those large uncertainties propagate through our ability to model ice flow. The other thing that matters is the geometry, the current geometry of individual glaciers. And I have two plots here. One is from a 2019 Farinati paper. And I love this one because this just simply shows the number of model solutions of individual small alpine glaciers, right? And so for the Himalayas, for Scandinavia, for Europe, there are a large number, 4 or 5 sort of like different models that have been run for these areas, New Zealand as well. But actually for Alaska, we only have maybe 1 or 2. For the edges of the Greenland ice sheet, maybe 1 or 2. And when you have fewer numbers of models, right, you have a smaller ensemble. That's important for understanding the uncertainty going forward. So that's one of our motivating factors. But another factor is when you look at models that have fewer observations going into them, they have overestimates or underestimates of the initial volume of ice. And when you have incorrect estimates of the initial volume of ice during the current moment, then you're unable to project that future mass change. And you can improve that by adding more observations, by providing more and better observations. And we really see this. This is from our initial concept paper that we published a few years ago, where we're looking both at snow accumulation and ice thickness. And when you are able to bias correct snow accumulation on a glacier, you're able to reduce the mean absolute error substantially by up to 65%. This is on Kaskawalsh Glacier in the Yukon, relative to other observations. And then this is a figure that was produced by Andy Ashwandon that's in our concept paper as well. But as you increase the density of bed observations, you can increase the accuracy of the glacier volume. Here you have the truth in dotted lines by reducing both the uncertainty and increasing the accuracy of the overall model output. So that is really what is motivating the need for the airborne observations in snow for flow, that the models that we have now have the ability, with the integration of more observations, to provide us better, more accurate, lower uncertainty estimates in the future. So what are we going to do? What is our operational strategy? And right, this is what we are planning to do. We're planning to operate. We have a plan for 3 campaigns in 27, 28, and 29. They're going to be 10 weeks long. We're going to be flying for about 300 hours per year on this beautiful Basler right here. We're going to be in 4 different locations in Alaska, in Svalbard, in Arctic Canada, and southeastern Greenland. We have 3 different instruments on board. We're going to have a microwave sounder, a high frequency radar sounder for ice thickness, and a scanning laser altimeter. In Alaska, we're going to be doing some in situ observations to measure snow accumulation, snow density, snow characteristics, as well as some other targeted observations. And we're partnering internationally to capture those observations in our international locations. And then our modeling requirements are actually core to Snow for Flow's mission. And I'll actually cover that here. So sorry, it's a little bit blurry, sorry about that. But as a NASA mission, we actually have science requirements, which the mission is expected and obligated to meet. We call them baseline and threshold requirements. That's not super important, but what we have here is they're based on sort of our science requirements are based on survey design, our snow accumulation, ice thickness, ice elevation, in situ snow properties, and glacier flow. But what I really want to call your attention to is that unlike a lot of previous airborne campaigns, the ones that I've highlighted in green actually require models to meet. So as part of our mission, we're incorporating both airborne observations, ground observations, and modeling requirements. So we, as part of our mission, are funding and are expected to provide modeling outputs that meet certain science requirements. And so to do that, we have a science team that has that we've funded. There are over 17 different universities that are part of our science team. We have an airborne component, a ground component, but also a synthesis and modeling team, and a range of international partners. So we've started conversations. We're planning for our upcoming season, and our synthesis and modeling team is very much involved in that planning. And you can see that here is how our mission workflow actually operates. Our team is composed of both observationalists and modelers from inception. And if I can get my pointer here, and just check the time. Right, we have our data collection and initial analysis, but then we have a large number of team members who are really focused on interpreting our data, but also using our data within modeling frameworks, including data assimilation, to provide both improved snow accumulation, snowfall observations, both in the retrospective period and during the forecast period, and actually provide us glacier mass change during our historical period and during the forecast period. So a summary of what our sort of campaign will look like, right? We're going to be flying in Alaska and in Svalbard in 2027. And then in the coming years, we'll be in Alaska again, and then in Greenland, and then finally in Greenland, and then Arctic Canada. And you can see the areas that we're going to be flying here. And each year will be focused on different areas and really focused on understanding each of these glaciers. And with the number of flight hours that we have, we expect to really substantially increase the coverage of snow accumulation and ice thickness measurements that we have across these regions by an order of magnitude or more. So how are we going to succeed at this? So the first thing that we need to do is we need to beat the melt. So that means we're going to be flying early. We're going to be flying in March and April in most of these regions before the onset of melt. The goal is to capture the sort of annual accumulation in each of these regions before we start to see any melt. And we're going to be flying low and slow, about 150 meters above those glaciers. That allows us to disentangle the surface clutter from the bed reflections. This is really critical with the high frequency radar that we are going to be using. We've made some improvements since OIB Alaska. We expect to capture more of the bed, more of the time. And we have a survey design that is designed to do that better and more frequently. So we'll be zigging and zagging across these glaciers as much as possible in order to provide a better, to capture the bed as frequently as we can. This will also allow us to capture variability in snow accumulation as frequent across these glaciers in ways that hasn't been captured before. And that's one of the things that we're interested in understanding is sort of how snow is distributed across these glaciers and how that might affect surface mass balance. So we're going to be having ground surveys in certain locations. This coming year will be likely focused on the Juneau ice field and up in the Alaska range. Our ground survey strategy is an interesting one. We plan on having a camp team that's really going to be focused on surveying an individual glacier very carefully, but then a roving team which will be going out and taking snow cores across multiple different glaciers. And the idea is to minimize the uncertainty that we have in our snow accumulation observations from the radar. And that's really important because going from our snow radar observations to SWE is one of the most important steps we can use that we need to make in order to use these observations in our models. This is a modeling webinar. And so I really wanted to talk about—
One more minute, Lauren.
Pardon, 1 minute? Sure.
Yeah.
Yep, I can wrap up pretty quick. So one of the things that I really wanted to emphasize is how synthesis and modeling are involved. And that's really synthesis and modeling operations come in flight planning, and very specifically, they are very much as part of that. And then they're actually as part of sort of our synthesis and modeling for the individual campaign years, and then also as part of our hindcast and projection goals. And then we have, our plan is to go from L1 to L4, and L4 is sort of a model product in both for snow and for flow. And so our plan here is really the workflow has both our observational data products and our model outputs. And so with that, I am on time.
Great. Thank you so much, Lauren.
Mm-hmm.
So thank you to both of our speakers again. So there were a couple questions for Paquita in the chat that she answered. If folks have questions and you want to raise your hand and or put them in the chat, go ahead. I will take the privilege of being a moderator to ask the first question while you're all thinking of some. So one thing I found really interesting was that Lauren, was that you had the modeling requirements, were part of the mission. And I wonder, it seems to me I've been more involved in atmospheric measurements than surface, but I know that in every campaign I'm aware of, things occur that you don't expect and you get, weather conditions you didn't expect or something. So how, and so like Paquita was talking about her golden case, for instance, that you can't really plan for ahead of time. I just kind of wonder how that fits into then these specific, like we're going to improve the model in this way by this much when you don't necessarily know exactly what you're going to measure ahead of time?
Yeah, so we actually had a lot of conversations about that, right? So our sort of baseline and threshold sort of percentages essentially are they're very achievable. Um, Even if, say, things go very poorly, we very much expect to meet those with the understanding that, we could, things might not go exactly as planned. But as you saw in the figure that I showed with the snow accumulation, right? The addition of actually very minimal data can reduce the mean error by 65%. So when we're talking about like 15%, we really expect to achieve those. And so we did have a lot of sort of back and forth with that, but it was this trade-off, right? Like if we don't include the models in our science requirements, right? Then in sort of like upper in certain eyes, they become less important and something we don't need to include, something we maybe don't need to fund. And so we really did want to include them as part of that and as part of our mission workflow. And so there was definitely that balance.
Great, thank you. Bob, go ahead.
Thanks. Really cool to see what's going on with Snow for Flow. And I guess my question is also related to trade-offs. With 300 hours, it seems like a lot of hours, but obviously you can't do everything. I was so hoping to see all of Greenland getting flown. And so I guess my question is, what were the pieces that went into your decision making about what you had to leave out in terms of where you were going to fly?
Yeah, so the areas that are chosen are climatically different. And so the reason why we're flying climatically different areas is that when you are modeling those areas, and you're modeling them, you're assimilating observations and you're using mass conservation, you tune the model to get at ice characteristics, right? And those can be, those tend to be similar across climactic zones. So by having different climactic zones, you are getting information that is relevant even for glaciers that you don't fly. So that's one of the reasons why we're sort of flying those areas. We're not flying all of Greenland, but we are flying areas where the snow accumulation is really high. And so that was sort of the option there. And we're flying Alaska, where previously the returns haven't been as great. So
Maybe a follow-on also is because I was looking forward to Icebridge Take Two, right?
yeah.
In terms of the zigging and zagging flight patterns, is part of that flight planning, will part of it be replicating some of the Icebridge lines?
So we will fly some of the glaciers that were flown by OIB. The goal is not to do OIB 2. We are currently looking at things. Joe is online, who is our current flight planner. If you have requests that are within our area, I would say email Joe. Don't email me. But yes, it would be considered as one of the many factors that goes into where we're flying. Yeah.
Great, thank you, Lauren. That maybe brings up a question that's kind of relevant both for Paquita and for Lauren. So Paquita, you mentioned in the chat that the modelers in the field helped you with flight planning and thinking about some of the ways maybe you were gonna what questions you were gonna address, or so could you just comment a little bit more on how, like, in day-to-day in the field, the modelers the modeler and observational interaction worked and what you thought was really valuable about it?
Well, we had a lot of time together in the field. We were there almost 6 weeks, and you may have noticed that we only got 8 flights off the ground. So this did give us a lot of time. Like those forecasting meetings that we had, those could go on for like 4 hours at times. Just the conversations that ensued for those that I hadn't really seen that happen before in a field campaign. It was very bottoms up with a lot of students were also involved in the discussions. So I think those connections that were built are pretty valuable. There's still there's modeling proposals being developed right now that are benefiting from that those long form conversations.
And Lauren, do you envision similarly that, I don't know if you'll have forecasting meetings in the same way, but how you'll do the flight planning in the field?
So we do it a little bit differently, right? It's really interesting to learn how atmospheric scientists do like in the field forecasting. So our in the field forecasting is really like, is it cloudy? Is it not cloudy?
I need
But
some
we actually,
atmospheric modelers to help you out there.
we do it much more in advance.
Mhm.
We are working with the modelers to essentially assess what are the uncertainties in like the models right now, and prioritizing what glaciers need to be flown based on the uncertainties in the model. And that sort of like allows us to prioritize them before we go in the field. And then sort of based on that, that's how we prioritize where we're based at a particular time. And we incorporate other factors in there. But it's a much sort of like earlier process. So we're not trying to capture a particular atmospheric, like fast moving, fast changing thing. It's much slower.
Mhm. But do you envision that you will have modelers out in the field during the observational phase?
We actually are, a lot of our modelers and observationalists sort of like integrate and do that.
Great,
Yeah, do both.
awesome. David?
So first off, thanks for the great presentations. This is a great session. I wanted to pick up on something that Paquita said in the first question, sort of also alluded to, and I appreciate the notion that we're not necessarily trying to repeat previous experiments in toto, but you did mention, Paquita, that one air-based campaign is not sufficient, and that implies that we should be thinking about better ways to integrate data and collaborate and plan these field campaigns so that we're at least collecting observations that are compatible with a sort of trajectory to advancing the research. And I wonder whether both of you, I'll bluntly ask you whether you have an ask for the Snow for Flow campaign. Are there specific measurements and observations that you're interested in collecting in the areas that Snow for Flow is planning on covering? And I wonder whether there's, and I think that was what the first comment or question was sort of alluding to too. Are there observations that we should be trying to share and collect continuously? And then I guess from since we have some program managers around the room and some agency representatives around the room, what can we be doing? Just ask a provocative question. What can we be doing to better promote the advancement of science through coordination and collaboration? How can we better support this? Thanks.
Okay, so there's a number of questions there and that's interesting. So Lauren mentioned that priority was cloud versus no cloud in the forecasting. So it would be interesting to have some measurement made on the plane that corroborates whether there was cloud or no cloud. And the radiation measurements in particular would be very valuable. I mean, your plane's not that large, so you don't have a lot of room for a lot of extra stuff on there. And I see Tristan Lecuyer is, or was. Well, at any rate, to my mind, if there was one thing that I would ask for, I think it would be the downwelling solar and infrared radiation broadband. So have a pyranometer and a pyrgeometer on the plane. That's at the top of the plane looking up, so you get those measurements. So that, and let's see, to continue, and then David, you asked about what program managers can be doing in overall. Having like a standardized set of measurements across all of these campaigns would be great. And maybe we do have that. The cloud physics probes tend to vary quite a bit between different campaigns. So they can't always be usefully intercompared. But maybe some like basis set of measurements that are advocated for on all of them would be good.
Yeah, I was gonna, maybe I'll ask a follow-up question. You had mentioned that workshop that the aircraft campaigns had, and I was wondering, are there like standardized data sets that are coming out of that, kind of standard products that all the campaigns will produce? And maybe that's a similar question for Lauren too. I don't know how standardized the data sets that, you're producing versus other campaigns in other regions might also do.
Yeah, so at that aircraft workshop, one thing we realized is that our data sets are not necessarily standard. And a good example of that is the ice nucleating particle concentrations. There's a couple of groups that are, in the leadership and that do all those globally, and they arrive at different conclusions. Some groups see many more aerosols than others. So there was talk at that aircraft workshop of doing some kind of instrument comparison to nail that down. And then with the cloud probes, that just needs labor to integrate all these different size distributions. And I do think people are pretty good at talking with each other. So that conversation I think will continue, because we're all kind of interested in knowing, do clouds change in the Arctic because of the aerosols that are impacting them, or because of these internal microphysical processes that are producing more ice, these secondary ice production processes? And I don't think we have the answer.
Lauren, you had a comment too?
Yeah, so one of the things that we do is that we have, strong data requirements through NASA. And that was actually one of the challenges as we went through sort of our approval process, was making sure that, that the models would fit within that framework well. I will say that we are working to make sure that our observational data sets fit within the data sets that have been previously collected. And that's an important part of what we do and what we are planning on doing. And that they're ingestible by models, right? That's a large part of our mission workflow.
And do you have more standardized instruments maybe? Where like just trying to understand again some of the
Yeah, so I don't
differences
know I don't know much about the instruments that were the sort of cloud particle instruments and like the range of options, right? We don't have that many options in terms of, say, high frequency, ice penetrating radar. So, yeah.
Pros and cons, I guess.
Yeah.
David.
So thanks for those responses, and I appreciate there's lots of fodder for future discussions, and I like the idea, especially as we start to get into more private sector, involvement in our observational development of our observational technology. I think something like an instrument intercomparison project might be something that we maybe need to think about. But Paquita, in your response, you also mentioned something that was really intriguing to me about something that just required a lot of labor. And I assume this might be, I'm not sure exactly what kind of data it is, but I wonder whether there's any consideration or thought about the utilization or application of artificial intelligence to possibly make progress on some of those super labor intensive projects. And I recognize that there's also a lot of labor that goes into developing a training data set to actually get to that point where you realize efficiency, but just wanted to see whether you had any thoughts on that. Thanks.
Yeah, no, that's already happening. It's the issue with these cloud microphysical instruments is well, one thing that NCAR does that I think is really nice is they bring the same instrument suite, or they have a basis instrument suite that they bring, and they process that in the same way. So that introduces a uniformity there. But the NASA campaigns, it's instrument teams propose to be on those campaigns. And so then there's less uniformity in those. And with DOE, I'm not as familiar with the DOE aircraft campaigns. I think you also bring the same suite to those campaigns.
Sort of a mix. We have a basis set, but sometimes we have some guest instruments as well.
Yeah. So there's pros and cons to both because the NASA campaigns are more flexible. You can get a, a range of instrumentation, whereas with the NSF ones, there's not as much room for additional instruments on the plane. But it would be nice to see those instruments that the NASA campaigns use together with the NSF ones and just make sure they're all measuring the same thing and get like the same numbers. And if you have that, then yeah, you can do a lot with AI. I mean, but the input needs to be something you have confidence in.
Yeah, and I
You're
think
not.
that brings up another question and another challenge, I think. So, right, you take these observations, any set of observations, it's going to take a while, a little bit of time to go through the observations, make sure they're good, the instrument was running well, it's calibrated, you're seeing, what you expect to see, so doing the QA, QC and the processing of the data. But then, of course, that's a challenge for the modelers. Do they want to work with preliminary data? Do they want to wait until the data is finalized? So I don't know if either of you have thoughts on that. And then that would probably be our last question because I saw that Hazel came on to remind us that we're near the end of our time.
Okay, I'll give one short answer and then Lauren can answer. Yes, so we are working on these value-added data sets, and in particular, the microphysical one will be valuable, which will be a complete, kind of a best estimate, and that's what we would like to hand off to modelers.
I think it depends on what the particular goal is, right? If you're using it for data assimilation, you want an observation that has well quantified errors, and hasn't been overly processed, right? But if you're looking for validation or something else, then maybe you want a level 2 or a level 3 type product. So I think it's really, I think what we have found as part of Snow for Flow and what I have found previously is it's really a conversation, like a continuous conversation to be had. And to sort of have that back and forth to really understand, what observations what need to be made and how to make them and what modelers really are looking for.
Yeah, so I think it goes back to that conversation, that interaction. Yeah, that's a really good point, which is one of the reasons we're trying to have these webinars to bring the communities together. So with that, I want to thank Lauren and Paquita again for their great presentations. And I will remind people these webinars are recorded and will be posted on the IARPIC site. So Lauren and Paquita, you can share them with all your friends and colleagues and other folks also. If you know colleagues who should have been here and weren't able to, please let them know. And then also the recordings of some of our past webinars on this topic that the teams have put together are also available. So with that, I think the MOMP team does not have a next webinar planned. We're taking an August recess, so look for more information from us in September. But until then, everyone, thanks again for joining and have a great rest of your day.
Thank you.
Thanks, everyone.
So
Good to
much.
see you all.